Continue with section 2.2 now, the limit of a function. We're just going to conclude by looking at a few more examples. Let's start with number 6, where we are given a function f of x, and it's a piecewise defined function. We talked briefly about these in chapter 1. The function says that we're going to have 2 minus x, and that's going to be the case if the x that we're looking at is going to be less than negative 1. And the function is just going to be x itself if the values of x that we're putting into it are between negative 1 and positive 1 inclusive. And once we get bigger than 1, we're going to be looking at x minus 1 quantity squared, that function. And that again is if x is, greater than or equal to 1. So actually we don't have equality on this one right here. We want to be strictly less than 1. So we want to sketch the graph of this and use it to determine the values of a for which. So we want to find out where does the limit as x approaches a of f of x exist. So, in other words, for which a is that going to be the case? And so you can see the only points that are going to be at issue here are going to be negative 1 and 1. Otherwise, the function is going to be defined and continuous at all other values of x besides negative 1 and 1. The points negative 1 and 1 are where we have these jumps in our graph. So let's go ahead and see if we can sketch a graph of this thing. We'll, again, not make anything too fancy here. But let's see, we're going to have negative 1 and 1 are two key points. Now, if x is less than negative 1, we have the function 2 minus x. Now, that's going to be a line with a slope of positive 2. Slope of negative 1, rather, and goes through positive 2. So it would be going through here at positive 2, a slope of negative 1, so that means it would go down 1 to the left 1, down 1 to the left 1. So it's going to be, let's see, goes to the point 0, 2, so let's see, with the slope of negative 1, down 1 to the left 1, down 1 to the left 1. Now see, it only starts once we get less than negative 1. So I'm going to put a hole right here, and then we're going to take off from there. So it's this graph right here. So it doesn't exist over here. That was just kind of a placeholder to see where we're going to cross the y-axis. So here's the line y equals 2 minus x, and that's the graph of the function for x being less than negative 1. Now how about this middle section if x is between negative 1 and 1, including negative 1 but not including 1? Well, it's just the line y equals x here. The line y equals x, of course, just looks like that. Now we have a hole here at, let's see, we're defined at negative 1 to be x. So f of negative 1 is going to be negative 1. But we have a hole right here. Okay, and then finally x minus 1 squared. Well, remember what that's going to look like. That's going to be the parabola shifted 1 unit to the right. And so if you think about the parabola in general, shifted 1 unit to the right, x squared shifted 1 unit to the right, but only defined for x being greater than or equal to 1. That means it's going to take over right here and go like this. So for what values of a does the limit exist? Well, does the limit exist for anything less than negative 1? Certainly it does, because the function is defined and continuous there. Does it exist at negative 1? Well, no, because you can see the limit as x approaches negative 1 from the left of our function f of x is equal to the y value here of positive 1, whereas the limit as x approaches negative 1 from the right of f of x, let's see, if we approach negative 1 from the right, we're on this green function, and we get closer to negative 1. What about the limits as x approaches positive 1 from the left? Well, as we approach positive 1 from the left, we're on this green function here, the center function, and we're getting closer and closer to a y value of positive 1. But the limit as x approaches positive 1 from the right, well, that's this blue function here, and we're getting closer and closer to 0 of f of x equals 0. Should have an f of x in here. Limit of f of x as x approaches 1 from the left, you can see, is equal to 1, whereas we approach 1 from the right, we are equal to 0. So where does the limit exist? For which a's does this limit exist? Well, we could say that the limit exists for all a except for a equals negative 1 and a equals positive 1. Okay, next problem I want to take a look at is number 11. We're asked to sketch the graph of an example of a function f that satisfies all the conditions. Now, the conditions to be met in number 11 are that the limit as x approaches 3 from the right of f of x comes out to be 4. We also want the limit as x approaches 3 from the left of f of x to be equal to 2. We also want the limit as x approaches 2 from the left. No, I'm sorry, as x just approaches negative 2. So x approaches negative 2. We want that to come out to be positive 2. We also want f of 3 to equal 3, and we want f of negative 2 to come out to be 1. So let's see if we can sketch this graph here. So we have some important values that we're going to need to look at. 3 is one of those values because we're looking at limits as x approaches 3 from the left and from the right. Negative 2 is one of those values. And let's see, we also want f of 3 to be something and negative 2 to be something. So here's negative 2, here's 3. Now I want the limit as x approaches 3 from the right to be 4. So if we come up 1, 2, 3, 4, as we come at this at 3 from the right, we want our function to be approaching 4. So let's see. We also want f of 3 itself to equal 3. So f of 3 must equal 3. That means we're going to be a point right here on our graph. So f of 3 is equal to 3 to satisfy that. Let's go ahead and satisfy f of negative 2 is positive 1. That's this right here. So that's satisfied. Now how about f of x? The limit as x approaches 3 of f of x is equal to 4. Well, that means as we come in from the right here, we want to be approaching 4. So we will come in here and we'll put a hole right here. So as we're coming into 3 from the right, the function value approaches 4. Now as I come at it from the left, I want to approach 2. So coming in from the left here, let's do that in red. Oops, sorry. Let's do it right here. As x approaches 3 from the left, we want to hit 2. So coming at 3 from the left, maybe we'll do something like this. So something like that, so that we're approaching 2 as we come in from the left, 2 being this value right here on the y-axis. So that satisfies everything about x being equal to 3. As we approach from the right, our limit is 4. As we approach from the left, our limit is 2, and the function value itself at 3 is 3. Now what about 2? Well, we want the limit as x approaches, what about negative 2? Limit as x approaches negative 2 to be 2, but the function value we want to be 1. Well, that means that the limit itself, as we come at it here, is going to have to be coming in to 2 from both directions. So we can come up, pick up here, and we want to be zeroing in on 2 here from both directions because we want the limit as x approaches negative 2 to be 2, and that means we want it to be the same from both sides. So as I come at it from the right or from the left, the y value has a limit of 2, but the actual function value itself is positive 1. So we have a little gap there, a little hole where the function is defined. Hope that makes sense. Finally, I want to look at number 22, where we're asked to estimate the value of the limit as x approaches 0 of the function 6 to the x minus 2 to the x divided by x, and we want to do that by graphing the function, and we'll state our answer correct to 2 decimal places. So we want to graph this function y equals 6 to the x minus 2 to the x over x. So you're definitely going to want a calculator or a graphing device or WinPlot that you can download on your computer for free. The program that I have here, I went ahead and plugged this in and graphed it, and you can see that we're a little bit bigger than 1 here. Let's see if we can zero in on that. So I'm going to try and put some values on here. It's a little bit messy right now. We're going to zoom in on this thing though. And so if you have this function on your calculator, you should be able to do the same. Let me see if I can zoom in. I think there's a way to do that. Yeah, there we go. So zooming in on this function. Now it is undefined at 0. Remember, look at our function. We're dividing by x, and we're putting 0 in for x. The function is going to be undefined. But as we zoom in on this thing, it looks like the limit of this thing as x approaches 0 is going to be 1.1. It agrees coming in from both the left and the right. We know that it's not defined at this point, so really there should be a hole in this graph because the function itself is not defined there. So it should be a hole right here, but it looks like graphically from zooming in on that thing that we have a limit of approximately 1.1. We can't say for sure, we can't say exactly. Now you can check that in part B by evaluating f of x for values that approach 0. In other words, in part B, what you're going to want to do is just try some values for x and then some values for f of x, 6 to the x minus 2 to the x over x. And just take values close to 0, like 0.1, 0.001, or sorry, 0.01. If you want, you can do 0.001, and a couple on the left side, negative 0.1, negative 0.01, negative 0.001 if you like. But just get values that are getting closer and closer to 0. And what you should see then, and when you put those values in for x, is you should see these values getting closer and closer to 1.1. In fact, for a couple of these, I'll go ahead and tell you what you should get. For 0.01, you should get 1.112353. For 0.001, you should get 1.099978. And so it looks like it's getting closer to actually 1.10. For negative 0.01, you should get 1.085052. And for negative 0.001, you should get 1.097248. So you can see that this thing, well, it does seem like it's zeroing in on 1.1. However, if you look at it coming from the right here, positive, we have 1.09, and coming from the left, negative, we have 1.097. So it's probably actually going to be more like 1.098, something like that. So not quite 1.1, because again, when your x value is positive and a little bit above 0, we're already at 1.099. So the limit is not going to be 1.1, because you can see we're decreasing a decreasing function here as we move from right to left, or an increasing function as we move from left to right. So it actually is going to be, if we were to continue to zoom in on this thing, we might see that we're actually going to be a shade under 1.1, the limit's going to be. And I don't know if we can get it tight enough. Well, yeah, you can kind of see it's starting to be a little bit under 1.1. But that bears out in our calculations here. Coming from the right at 0.001, we're at 1.099. At negative 0.001, we're at 1.097. It's going to be somewhere in between those two things. So we guess 1.098. We can get more and more degrees of accuracy by, well, by taking values of x that are closer and closer to 0. For example, you could keep going and you could go 0.0001, negative 0.0001, and you would see the accuracy start to come in there with more and more degrees, more and more places to the right of the decimal that get fixed. Alright, so that should be enough information to get you going on your 2.2 homework. And as always, if you have any questions, let me know. Password for 2.2. Password is going to be iconoclast. It really doesn't have anything to do with this lecture. What it means is a person who attacks subtle beliefs or institutions. So iconoclast is your password for 2.2. Good luck, and again, let me know if you have any questions.